So I have 45 minutes to talk to you about waves, and I could talk forever. And I've just seen the students revising my chapter, which they just told me there's just too much stuff in your chapter. So I'll try to go to the essential things. So there's basic things, because we've all seen waves, right? So just look out and you see waves. Sometimes the program is called surface waves. Most people would call them wind waves because they're generated by the wind. And I'll just call them waves because that's what people would think about waves. It's just waves generated by the wind in the ocean. So I'm not going to talk about tsunamis. I'm not going to talk about tide. I'm not going to talk about Kelvin waves and stuff like that. But mostly waves generated by the wind. Okay, and this is just an example of a nice picture you can get from Sentinel-2 over the Bay of Pollença. So the resolution is hard to see, but if you actually take the slides and click on the image, you'll see the full image across the Mediterranean. This is a reflection of the sun on the surface that shows you the wave patterns. And oh yeah, I forgot to present myself. So I'm Fabrice Ardhuin. I work at the Laboratoire d'Oceanographie Physique et Spatial, so it's ocean physics and satellite remote sensing in Brest, in France. And it's very special for me to be here because actually I was a student in University of Mallorca 20 years ago. I was doing a project together with Joaquin, and I could feel his passion. And that's actually what started me to do then a PhD in California in oceanography and working on waves for the last 20 years or so. And since I'm not supported by the school, I have to do some advertising to support myself. So we're hiring people. We're actually hiring a full professor next year for working on ocean and climate. Associate professors a year after that. There's a postdoc and PhD position open, especially working on waves and sea ice and waves and current interactions. You can come to me and talk about that. I'm going to be leaving tomorrow morning, so if you want to talk, it's going to be tonight or early tomorrow at lunch, breakfast, for example. We're also doing some training on waves, so if you really want to know more about waves and know actually how to run the Wavelets 3 model, which I'm actually a big contributor of, you're welcome to come to Brest. We're doing some training sessions there. And we're also in the business of doing some forecasting and nightcasting. We've been doing that for the last 15 years or so. And it's actually a great experience to work together with ECMWF and compare every month the output of our runs to their output and get some interesting feedback. And we've been pushing them for the last 10 years to improve on their parameterizations, because as I will show you, one of the key of the wave models is how you parameterize all the things that we cannot represent explicitly, like wave breaking, for example, is parameterized, and actually that can improve a lot the results. And you can look at all these data. So we have a bunch of data on waves, salinity, and other things. All right, let's go on. So I'm going to talk about waves, just some basic definition to begin. Talk about sea state. What is sea state? What are waves? Energy, momentum. I'll introduce what are wave spectra, which is the way we represent waves. What are the wave models good for? And don't have much time to talk about coupling. So if you want to know more about that, we can talk after. I'm sorry for that. I'll show some nice examples of wave observations. And I'll finish with what's been taking me a lot of my time since a year and a half, which is a proposal of a new satellite which is called SKIM. And I think it will be interesting for you also to learn how actually people come up with ideas of satellites and how actually they get launched in space. And actually, if you have some ideas, ESA has an open call for new ideas. So you can have planning letters for December and a full proposal for next March. And if you are selected, your satellite can go to space in 7 years from now. So, if you have ideas, why not? There's a lot of people doing nanosats these days, small things. You could do constellations, many other things. So it's all really open. And there's more material. So I'm in the process of writing a book. I've been doing that for the last 10 years. So it's slow progress. So I'm adding one chapter every summer, something like that. And so you can find it there on ResearchGate in particular. Okay, so waves play an important role in the Earth system. It's a strange thing because waves actually have some motion in the air, some motion in the water. People usually think only about the motion in the water, but actually the air is moving above the waves. And so these motions at the air-sea interface are very important for defining fluxes, and Mark Bourassa touched on that. They're also very important at the land-sea boundary, coastal erosion, any damage on the coast, extreme sea level, storm surges. All these are associated to waves. There's a lot of work now going on studying the interaction of waves with sea ice. And I don't have time to talk about it today. And also some funny stuff I've been working on also for the last 7 years is actually waves make seismic waves. So the ocean waves you see, they are also radiating seismic waves from the middle of the ocean. And as you are sitting here, you're actually moving up and down by a few microns every second. You don't feel it, but if you put a seismometer, the main signal that is recorded by seismometers are not earthquakes, but microseisms coming from ocean waves. And just to give my own flavor about this scale diagram, so we've been seeing this kind of stuff going from small scales in time and space. And Baylor was pointing out that people focus a lot on this, what's happening on the diagonal, which is essentially, if you actually are on a given slope here, you actually have a typical speed, and that would be the advection speed by currents or stuff like that. But waves actually have some obliqueness to that because of the dispersion relation. So different scales in space are related to different scales in time, and I'll come back to that. And the way we actually observe currents these days, there's different systems for measuring currents at fixed position, just very local HF radars on the coast and drifters. And what we want to do with the SKIM satellite is actually measure currents over a broader range of scales in space and time. So this is some pieces. And also I want to find out that even wave by himself, wave by wave, the time scales is a few seconds, typically 10 seconds. But waves also change on climate scales. There's a sea state climate which is changing over centuries. So when you think about scale of waves, it's not just all this in the small scales. It also is large scale here. The waves are changing with El Niños. There's a very strong correlation between wave height and El Niños, for example, in the Pacific. And there's a pretty strong concern about change in the wave climate in the future. Is wave height growing up? Is it going down? And what's going to happen for the coast? So it's not just sea level rise, it's also change in storms in the future, which is important. And yeah, I'm just going to skip that one. So what are waves? So when you think about waves, you think about the surface moving, and that's a movie acquired from a research platform in the Black Sea. And you can see the image from the camera on the left, and actually we had 2 cameras doing a stereo reconstruction. And when you do this 3D view, then you can actually make this map on the right here, which the blue is a trough, the red is a crest, and that corresponds to what's happening here. So here you have a crest passing by, it's going away, then you have a trough. So one red blob, like this blob here, you think, okay, that's a wave, that's one wave moving away, okay? And yeah, I don't have much time, don't have the time to show it to you, but I encourage you to go and see that movie, which is a movie of the Waves Across the Pacific experiment from Walter Munk in the 1960s, giving you some introductory material about waves. It's a really amazing movie, which was part of my inspiration for working on waves. These guys going in the middle of the Pacific and looking at waves coming from storms from far away. So waves, one wave is like that, okay, but you also have, it's not just a simple shape, and this is very famous painting shows, okay, a big wave, but then on top of this big wave you have very small, tiny wavelets, okay? So what I want to introduce to you is a notion of sea state. And so the sea state is a collection of all these waves, large and small, with small wavelengths and large wavelengths. And for each of these waves, you can define a wavelength, which is a distance between 2 crests, and a time between the passing of these 2 crests, which is a period. But you don't have just one wavelength and one period at a given time. You have all this collection of different wavelengths and periods, one on top of the other, like here, very short waves on top of a large wave. These long lengths and periods are related for each individual wave by the dispersion relation. Approximately, this is given by a solution for the linear waves. So you take the equation of motion, Navier-Stokes, and you simplify them. You end up with this relationship in which the wavelengths goes like the period squared. And so engineers would call that Froude scaling. And it's a very important concept that if you actually double the period, you're actually going to multiply the wavelengths by a factor of 4. And to give you some idea, 10-second period wave has a wavelength of 150 meters, which is 1.5 football fields. So 10-second wave, it's actually pretty long. So it's longer than a typical ship. And that's true for deep water waves. In general, the depth comes into the picture, and so you have this hyperbolic tangent function coming in, and that's what you get. So one very interesting thing is this relationship between wavelengths and period. You can also look at the phase speed, which is the speed of a given crest, so the ratio of the wavelengths and period. So on this animation, I've made a C state, which is a superposition, a sum of two monochromatic waves. So I have a black wave train and a red wave train, and I've labeled the crest with a red and a black bullet, and they're moving from left to right, and you see that it's going to appear here again. So at the beginning, they are together, and because these two have very small difference in wave period, one wave train is traveling faster than the other, okay? And the sum of the two is a blue line. And so when you make the sum of these two frequencies with almost the same frequency, you create this beating pattern, which are what people call wave groups. And you can see that the groups do not travel at the same speed as the crest. And the speed of the group is the group speed, and it's given by the derivative of this radiant frequency with the wave number. So k is the wave number, 2 pi divided the wavelength. And in deep water, what we find in that case here is that the groups have the speed which is half of the phase speed. And for wave modeling, what's actually very important in the open ocean, we're not going to track each wave one by one, because we will need a very big computer to do that. What we're going to track in the wave models is the energy, as the energy is traveling at the group speed. Okay, so a few things about wave motion and the relationship between the energy and the elevation. So this is a case showing in color the, what is it? The non-hydrostatic pressure. So if you take the pressure, remove the hydrostatic pressure, you get this pressure difference. So waves are not hydrostatic in general. And you can see that you have some small arrows, which are the velocity field. And you can see that the arrows actually are along the isopressure contours. So we have the balance between the pressure gradients and the centrifugal force. So it's a cyclostrophic balance. So the water particles go around the pressure, along the pressure gradients. And as the wave travels from the bottom to the, so here at t equals 0, and then a fraction of a wave period later, you see the waves moving and the particles go forward. If you actually track water particles, they do this motion here. So they almost go back to the same position, but not exactly. And this difference between an exact motion going back and this small drift is what is called the Stokes drift. So the wave particles do a circular motion plus a Stokes drift, and the wave particles actually go forward as a move with the waves. And this drift is relatively strong at the surface, but then you can see as you go at depths, so this is from the top here, z equals 0 at the surface, and this is at the bottom. You can see that at the bottom, the water particles are almost exactly elliptic. All right, so the motion looks like this. If you compute the kinetic energy and the potential energy, you see you would have half and half, so half kinetic and half potential. And of course, you have energy everywhere. So one way to normalize that is you look at the energy per unit surface. And so this will give you something which is the density of the water times gravity times E. And my E here, wave people call that energy, but this E is the variance of the surface elevation. So it's it takes surface elevation minus the average, and you square that. So it is, for this cosine wave, it's just a squared divided by 2. And it has units of meter squared. So this is what often people call energy, but the real energy is rho g times this, and that one has units, proper units of energy, which are joules per meter squared. The E factor is typically of order 1 meter squared, and the stuff in front is 10,000. So there's a lot of energy in waves, right? So typically, you're getting tens of kilojoules per meter squared, and some people want to actually use that energy for light, for power. The issue is that you have to put a device in the water that's able to take energy when the waves are small and able to resist the big storms when big storms come, and so it's actually a very big engineering problem. But potentially, you could take terawatts of energy from the waves in the ocean. But in practice, I don't see it coming anytime soon. All right, so waves contain energy. They also contain momentum. And the fact that they contain momentum is related to this drift of the water particles. On average, the water particles go forwards. They move with the waves. So actually going this way in my plot. And the expression for this drift, so in deep water it looks like this. You have the radiant frequency, sigma, 2 pi divided frequency, the wave number, the variance of the surface elevation, and then the exponential 2kz. So it decays vertically with depths really rapidly. And when you integrate that for all depths, it will be always this mw is the momentum of the wave field per unit surface. It is the wave energy divided by the phase speed. And this relationship is very profound in physics. You actually have the same relationship for light photons. The momentum of photons is P is energy divided by the speed of light. Okay, that's true also for internal waves. Internal waves also have momentum. And as soon as you have wave energy, you also have momentum. And since momentum of the waves will be interacting with the momentum of the current, and unfortunately, I don't have much time to talk about it. It's related to what Bader was saying on Monday, but that's going to be for another talk. All right, so time and space scales, what you have. So I'll just show you this usual plot of the energy as a function of time, taken from Walter Munk. So typically we have a very short time on the left and long time on the right. And what I'm going to talk about today is wave generated by the wind, which is in this box here. I will also say a few words about this band here, between 30 seconds and 5 minutes, which are not generated by the wind directly, but are generated by the waves here on the shoreline. They become nonlinear and they transfer energy from this frequency band to that frequency band. And these are called infragravity waves. And they are pretty important for coastal applications. And possibly also important for the noise on the SWOT mission, because they have a typical wavelengths of 50 kilometers in the open ocean. And their amplitude is typically half a centimeter or a centimeter. If we take a wave model, we actually are computing this spectrum. Now it's more quantitative, and you see, this is now the energy, or this variance of the sea surface elevation as a function of frequency. The different curves correspond to different time step at a different point in the ocean. This is just off the Oregon coast. I just took it for, I just picked a point in the ocean. You can see that the shape of the spectrum, it's a log scale. Okay, so this is a very big change in energy, going from 10 to 10 to the minus 4, basically. So it's in dB. So you see at high frequency, it's always more or less the same shape. In the middle here, you have usually a peak or 2 peaks. The peak at high frequency is usually the wind sea, which is a wave generated by the local wind. And at lower frequency, you typically will find swell, which are waves coming from storm far away. So imagine you have a big storm somewhere which is making some wind sea, and this wind sea is going away, radiating away from the storm, becoming swell, and then away from that you record it as swell in this, at that location. And then you see at these longer periods the infragravity wave band with much lower energy and more or less always the same shape. And so for scale, so here's a 100-second period, and here it's 10 seconds. Some real example of this, we put some pressure gauges on the cliff. So the blue pressure gauge here is giving you the blue time series. Here it goes on for 9 minutes. And the red gauge on the top of the cliff is giving you the red time series. And a zoom of that is given here. So if you only take this part of the plot, it's only 2 minutes. And you can see you have normal waves, which this peak in the blue and going back and forth. And you can see the waves also on the top of the cliff. But you also see the water level rushing up for 2 minutes, staying up for 2 minutes, and then going down. These are the infragravity waves. And this is an extreme case of infragravity waves with an amplitude of 2 meters on the cliff. And for scale, so I'm here talking to some people, deciding where we're going to put the instrument. And this is, yeah. And actually, we went to that island because there are rocks on the top of the cliff which are moving during big storms. And these rocks are actually 10 meters above the tide. And imagine what's happening is that the waves are pushing water on the cliff, and the water is being bursting on these rocks and then moving them away. So the typical sea state you would find are very different. Sometimes you can have very short waves, like on that day you can see there are shorter waves. Here it's more longer stuff. You can see wave breaking in white. This is stereo video. The spectra corresponding to these 2 days are shown in the bottom. So in that case we had some longer waves here and shorter stuff here, which are the ones you can see here. And here it's only the long waves you can see. Here actually the wind was stronger, and this is where we had white caps. So the information contained in this curve, this wave spectrum, is really telling you something about the shape of the sea surface. And it's a bit different, and I'm not sure I should talk about that one, but okay, now I have it. If you take a time series of tides, that's a typical NIP spring-tide cycle, and you do some tidal analysis on that, you can actually reproduce this curve with only 2 or 3 components, and the spectrum of this tide is actually this M2, S2, and on all these frequencies around the semi-diurnal tides. If you actually zoom in on this peak here for a few minutes, you get this time series in blue here, which is much more confused, and there is no way you can reproduce waves with only a few components. So the wave spectrum have a broad band, and there's every energy throughout the spectrum, whereas the tidal spectrum has really discrete, sharp peaks. And so in order to represent this, we cannot use amplitude and phase. We're using spectral density. And so what's important is that in the end, the spectrum is normalized in a way that the area under the curve, so the area in black, gives you back the variance of the sea surface. So the sum of E of f by the spectral density times df is the variance of the sea surface elevation. And we define the significant wave height as 4 times the square root of the variance. So when you compute a time series or measure time series, you get the variance, and 4 times square root of that is what we call the significant wave height, which more or less corresponds to the visual impression you would have of the sea if you watch it. You say, okay, well, the scale of the wave is that, and that's typically this kind of number. All right, so here I was showing you, spectrum from time series. And actually, the sea surface elevation is not just a function of time, it's also a function of x, y, the horizontal coordinates, and time. And so in general, you could have a spectrum in 3 dimensions. But because waves are essentially linear, we can reduce that to 2 dimensions. And here's one example showing you the energy in colors as a function of direction going around the circle and frequency going away from the center. So the short frequencies, which are the long periods, are at the center. And outside, you have the shorter wave period, which are the higher frequencies. And so here you see you have 3 blobs of energy. You have a big blob here, which I number 3, actually corresponds to the effect of the local wind, the wind sea. And the other 2 blobs are swells coming from faraway storms. And if you actually take each of these dots or a quadrangle in my plot and make a sinusoidal shape on that, and you sum them all together, then you end up having something which looks like the real sea. It's just a sum of all the components. All right, so much for spectra. And one thing I want to tell you is, yes, this wind sea part is, it's actually what's the source of all the different wave spectra. At some point, the waves is a wind sea in a storm, and the wind sea grows in time and space. And it takes time for waves to grow because what's happening as wind's blowing, most of the energy is not kept in the waves. It's being given back to the turbulence of the ocean, and the momentum is giving back to the currents. So the waves is a very transparent filter to this wind forcing. As a result, the momentum and energy is only accumulating very slowly. So it takes typically a couple days and thousands of kilometers for waves to reach large periods and very large wave heights. And this is typically showing the wave energy growth as a function of what is called fetch. So fetch with the distance over which the wind is blowing. All right. So just basic wave things. We have a 2D spectrum that represents the distribution of energy as a function of frequency and direction. You can actually use this 2D spectrum to give statistics of the full 4D wave field, in space, vertically, and time. And the sea state in general contains wind seas driven by the local wind and swell coming from wind somewhere else, which has been radiating to your area of interest. These can be identified pretty well. I was showing you before. You have these blobs of energy in the 2D spectrum. But you have to be careful that there's actually different definition, and ICMWF is using something different from the rest of the world in terms of defining what is wind sea and swell. So always be careful if you take some wind sea and swell parameter, how it's being defined. And just also one comment here, a lot of people are using peak periods for parameterizations. Well, okay, if you take the peak period for that case, it's going to be this peak right here, which says nothing about the wind sea right there. So be very careful if you use peak periods in a parameterization, usually it's a recipe for disaster. So try to rather take the WinC partition and do some averaging of the wave energy there, or wave period. And yeah, the WinC is growing with space and time. All right. Just want to say one thing about homogeneity. I was discussing this 2D spectrum. You can actually look at waves at scales shorter than the wavelengths, and you can actually run a wave model phase resolving, phase averaging at a scale shorter than the wavelengths, because wave travel in time, and so it doesn't really matter that the wave energy is changing over half a wavelength. It's actually can do some average and actually compares to the observation pretty well. This is just a comment on what you were saying the other day. So how do the wave models doing? How are they good for anything, and what do they do? So I will only talk here about phased average models, in which we compute the energy of these different components of the spectrum. And these are typically Wavelets 3, which I work with, SWAN or Mike or other things. And what they do is that they take the 2D spectrum and they involve it in space and time. So we actually have 5 dimensions. So we have frequency, time, x, y, no, frequency, direction, x, y, and time. So because of that, wave models are memory intensive. And for example, ECMWF have a wave model coupled to the atmosphere since 20 years ago. And the atmosphere and the waves don't fit together in memory. So at each time step, they have to empty the memory, put the waves, empty the memory, put the atmosphere, just to give you how crazy it is. So we have this very big, massive thing. And so we have to discretize these space in spectral space and in X and Y space. So typically, we cut the frequency band in something like 30 frequencies between 0.035 hertz, which is around 30 seconds, and typically going almost to 1 hertz, so 1 second waves. And depending if you have more resources or not, you may use 24 direction, 36, or even more. Recently, I've been playing with adding very low frequency waves into the wave model. So I've been adding like 20 more frequencies going to 300 seconds in that range. And it's kind of fun, but it's very expensive. So it's only for research so far. And maybe we actually will run that operationally for SWOT to predict, give some flagging for infragravity waves on the SWOT altimetry data. So we're having, essentially, we're predicting the shape of these spectra and involving that in time. And if, that's a 2D spectrum in frequency and direction. If you make the sum over one circle, so integrate along the circle, you go back to a 1D spectrum in which you only have frequency. And here are some examples of a model spectrum in blue, the observations in black. And that's typical that there's some mismatch between the model and the observed. If you actually take the sum of the entire energy, which gives you the wave height is usually pretty good, but the spectra can be having some problems. So that was for spectral space. Then for spatial resolution, there's many ways to cut up space. So we're only dealing with horizontal space because these are surface waves, so we don't have to do vertical discretization. So it's only a 2D spatial decomposition. People have been using historically regular grids, so take longitude and latitude in regular delta longitude, delta latitude of half a degree, quarter of a degree, what you want. For coastal applications, we use a lot triangular meshes, and we've been using that for the last 10 years. For the Arctic, these constant longitude and latitudes are not very nice, so just nice curvilinear grid or what's used for ocean models is pretty good also. And you can also use quad trees, which are these squares that you cut up in pieces and stuff like that. And actually, Wavelets 3 has all these 4 different options, and you can mix them and match them and have two-way nesting of all the different grids. You can have a lot of fun. And to give you an example, these are a snapshot of wave model for the North Atlantic. So you see the UK, France, and Spain. Zooming in, or the Brest region around the island, zooming in again, and zooming again on a small island, and then you get up with these triangles here, end up like being a few meters across. So you can do all these scales with the same model and burn up a lot of CPU time. And just to show you that it actually works even on the beach, this is an example from Duck, North Carolina, on the US East Coast. There's pressure gauges on the bottom, and this is you have a bar, and the water depth goes from 0 to 5 meters, and you have only 300 meters across. And these are comparisons of Wavelets 3 run on that scale with a couple of meter resolution compared to the observation. And it's not too bad. And there's actually more detailed of this kind of wave breaking in shallow water with SWAN done by Salmon et al. When you do this, with the phase average model, the only problem you have compared to reality is that your sea level is fixed over your time step, and you're not resolving the fluctuation of the sea level with infragravity waves that would give you drying and wetting at the beach. And so you're missing some of the action, but that's then if you want to go beyond that, you have to go to phase resolved models, which Alejandro maybe will talk next week, but maybe not because I think he has other obligations. So what the equation we solve is something like this. We have this wave spectrum changing in time. We propagate it with its group speed. We advect it with a current. We refract it, meaning that the waves turn because they go into different water depths or go with the current. And all this stuff then is changed by a source term on the right-hand side. So this is a radiative transfer equation, or you can call it a transport equation with a source term. So it is hyperbolic. And the big difficulty numerically usually is this bad guy on the right-hand side, which can be numerically stiff, which means that it can have very small time scales, and so you need to integrate that nicely to have all the right behavior of the spectrum evolution. To get good results with the wave model, well, this term here has the effect of the wind. So wind is making waves, and so we have some wind speed coming into the wave model, so reading fields from ECMWF or NCEP. So first of all, you need to get good forcing fields, and the first one you need to get right is the wind. If the wind is off by 10%, you're going to have the wave height off by 15%. So if you want to know if the winds are good or not, you take a wave model and run it, and you'll see if your wind field is good. The other aspects, which is very important in wave models and which makes big differences between different models, is parameterizations and how you actually compute this S term on the right, which contains the effect of the wind, the effect of wave breaking, which usually we write is as, so in is wind inputs. This is in nonlinear interactions because waves evolve nonlinearly and that changes the shape of the spectrum. You have a dissipation term due to breaking, and then many other terms, the effect of the eyes, the effect of the bottom, the effect of anything, whales, or you can invent your own source terms, and you have many options. And so in Wavelet 3, for example, you have these two terms are paired together, so input and dissipation usually are made to balance one another, more or less, and so you have options going from ST1 corresponds to what was called WAM cycle 3, and my own version is called ST3 in Wavelet 3, and then the bottom special thing we do with ripples on the bottom, changing the roughness of the bottom, is BT4, and many other things. So I'm not going to detail that. If you're interested, you can go in the Wavelet manual. We did a nice synthesis paper with Aaron Roland a couple of years ago in Ocean Dynamics, and this was a very interesting comparison by Stopa et al. Of these different parameterization in ocean modeling last year. And finally, you have to do some numerical integration. Now, a lot of people have invented crazy numerical schemes to do that right. And my sobering remark here is that ECMWF are still using a first-order upwind scheme, which is super diffusive and really has bad properties. And they have a growth limiter with a very big time step. And the results are almost the same as what we do with crazy third-order schemes and whatever. So whatever. You make efforts, and that doesn't really pay in the end. So this plot shows you results from Wavelet 3 run at half a degree resolution globally for 1 year, and these are statistics against altimeter data. So where it's blue, the model is good, and the error is typically around 7%. RMS difference between compared to the altimeter. And where it's red and orange, then the error or the difference rather, go up to 15–20%. And I say difference because here, actually, in this Indonesian seas, the wave height is very low, and so the altimeter actually is pretty bad. So altimeter wave height below 1 meter are really not good. So in that case, it's not just the model is bad, it's probably also the altimeter wave height is not very good. And you can see, places are more or less good. So here, it's really the ice, which is causing some problems. In this model, we don't have any currents, so you have the effect of the Agulhas current here around South Africa. I also point out here that, we also get hurricanes, like a couple of weeks ago. And winds in hurricanes at ECMWF, they're really underestimated. And so that causes some bias. But on this kind of global plot for an entire year, you don't see it because the hurricanes, they only come a couple of weeks in a year. Yeah, so you have to put that in perspective to this is normalized in percent wave height. So these are the average wave height. And so to give you some idea, the average wave height globally is actually maximum in Southern Ocean. And actually, yeah, I first have to do my quiz here. So, so where are the biggest waves in the ocean? So if you believe it's in the North Atlantic, you can raise your hand. If you believe in the Southern Ocean, who thinks the Southern Ocean? Yeah. Or in hurricanes and typhoons, who thinks the biggest waves are in hurricanes and typhoons? No hurricanes, nobody is hurricanes. So the biggest waves actually are in the North Atlantic in big storms. And the reason for that, but they don't come very often. So on a yearly average, you don't see it, right? So on average, during the year, the maximum is like 5 meters average. But the biggest waves you actually find here between Greenland and Iceland. And that's because in that region, storm comes once in a while that actually follow the wave groups at the same speed. And so these pretty strong storms actually amplify the waves as they travel with them. And that gives wave heights up to 20 meters. That was recorded by Jason 2 a couple of years ago. And typhoons and hurricanes, they don't give such big waves because the fetch and the time scale is too short. To have big waves, you need to have large fetch and large time evolution. And hurricane high winds is just too small to make big waves. And we're doing this validation, so I've been part of this validation with ECMWF for the last 10 years or so, and that gives you the scatter index for winter and summer. And you can see the bottom curves here in the winter ECMWF, and we're getting almost the same. So that's my model, is a dotted blue line. And the CMEMS global model run by Météo France is this other purple line here. And in the summer, you can see clearly, and it's also true in the winter for the 5-day forecast, that the best solution is actually the CMEMS, which uses ECMWF winds, the parameterization from my lab, and data simulation that they do using satellite altimetry and SARS. So models are pretty good for wave heights, but they're not so good for spectra. And this is, I'm going to skip that. But typically, you can have biases at low frequencies that can be 50, 100% in coastal areas. This is a scatter index on the end of the wave height for waves longer than 10 seconds, which are very important for shipping. So this is actually off Rotterdam Harbor, and they're trying to improve that, and it's a big problem because ships getting to Rotterdam, they roll with the waves, and the big ships, they don't like these very long waves. And this is not well forecasted now, so we have this RMS error of 50%, so almost no scale. And directional properties, yeah, these are some Taylor diagrams of the quality of different wave parameters. The wave height is in black. M2 is like the orbital velocities, which is good, important for engineering. TMO2 is a period associated with that. SPR is directional spreading, which tells you the waves go all in the same direction or go in very different directions. And this is with these two different parameterization in WaveRS 3. And you can see that the worst parameter is actually this directional spreading, which gives a correlation around 0.5. And we actually have a hard time getting the directional spectrum right. So we actually hope to get good data with CFOSat, with China-France Ocean Satellite measuring directional wave spectra next year to be able to understand and look at these things and eventually come up with better parameterizations or possibly assimilate the data to correct this. And does it matter, directional spreading? Well, yes. This is a run-up on the beach normalized as a function of the width in frequency of the spectrum, and the colors are directional spreading. So if you take the same wave spectrum and just make it broader or narrower, you can actually increase the maximum water level due to waves on the beach by 50%. So it's directional spreading is actually pretty important for coastal applications. Okay, I'm going to skip that. And let's say, yeah, one thing I would say about small scale and currents. So as I told you, waves are driven by the wind, but they also are influenced by currents. And this is one example of altimeter track, altimeter path going across the Gulf Stream. And you can see in black and green, two different processing for the altimeter product. You can see it's actually pretty noisy, and the noise depends on the processing you do. In blue, I have my model, which is not using any currents, so it's just missing this big, here the wave height is increased by a factor 2 as the nor'easter is blowing against the Gulf Stream. And if I actually put the current from my VISO in the model, I get this red line. So I get something, but it's really far away from what actually is observed. So what is wrong? Is the wave model wrong, or is it the currents that are wrong? Well, my guess is that the currents lack a bit of a gradient, and that would take another talk to explain that. But we actually started to look at the spectra of wave heights, like Rosemary was showing for the sea level, for this SSH. Now we also look at that for the wave heights. And this is where you see that if you actually take a model without any current, you get this curve in black. If you put current from a pretty high resolution ROMs with some isoscales and everything at 2 kilometer resolution, you get a spectrum which is in black. And the corresponding wave-height spectra would be something which is the green light symbols, which more or less matches. The other one is for a different season in the winter. And the black and the difference between the black and the green is different processing. So what's happening is that at small scales, most of the variability in wave height is buried in the noise due to the processing. And this is what it looks like if you just take some snapshot of a wave model in the Drake Passage between Chile and Antarctica. This is a snapshot from the MIT GCM currents at 2 kilometer resolution. If you take WaveWatch without any currents, you get this kind of map of wave heights. It's nice and smooth, just due to the winds. And if you put the currents, you get these much sharper features, which really look like the features in the currents. And you have this region of high waves and low waves as the winds are blowing against the current here. So what's happening at small scales in open ocean, typically less than 100 kilometers, is that the surface currents are actually dominating the gradients in the wave height. And as I said, I have no time to talk about waves in ice. This is a picture of a buoy in pancake ice. So the pancakes here are about this big. And the fact that the ice looks like this is because you have waves. If you had no waves, you don't have pancakes. And you can imagine that in the Southern Ocean, you have hundreds of kilometers of pancake ice. And so waves do have a big impact on the sea ice. And there's a lot of work going on now also in the Arctic, because the Arctic is changing very fast. And we started to see much more pancakes in the Arctic, in the Beaufort Sea, for example. And that's actually the picture from a cruise in the Beaufort Sea a couple of years ago. But we still have how to model that. The interaction of the ice and the waves is still ongoing work. And one thing I wanted to show you is some nice example observation of waves from satellite imagery. I'm sure you've all been through Google Earth and looked at different regions of the world. This is Gibraltar Strait from Sentinel-2. These wave-like features actually are internal waves, as you can see at the surface. And you see the internal waves because you have currents associated to the internal waves which are changing the short waves riding on top of them. If you zoom in on the internal wave, you see now the actual wave fronts. You see this kind of crisscross pattern. And here you see the front here and the waves changing on the front. So these are nice, pretty pictures. And you can actually do some quantitative analysis of that. And this is an example of a piece of the ocean with waves in it. You take a Fourier transform of that. And what's very nice with Sentinel-2 is that red, blue, and green are not taken together, but separated by like 1 second. So you can look at the waves and you see them moving between the red and the blue. And this displacement of the waves between the red and the blue, you can analyze the speed of these waves, and you get a phase speed as a function of wave number. This line on top here is a dispersion relation I had before, and it's all shifted due to a current. Essentially, the phase speed is just the phase speed I had before plus the current. So you can actually measure the current vector with Sentinel-2 imagery. And if you take Aviso currents plus all the Sentinel-2 imagery on top of that, you can see much higher currents, which are much stronger gradients. And you can actually start to map currents at very high resolution from space. So that was a fun part, and I guess I'll have to skip SKIM and just say a few words about that. So SKIM is a satellite project which is designed to measure currents and waves from space. And it's not using altimetry, it's using Doppler shift. And Doppler oceanography actually works. We've done that. This was work done 15 years ago using Envisat data. It's not been published because we moved on something else and Envisat died. But what you see is drifter velocity is projected on the east-west direction. And on the bottom is what you get from Envisat Doppler shift. Taking many, many images and doing some average at the same time. You can see very nicely the eddies in the Alboran Gyre. You can see the circulation in the Black Sea. So you can actually measure velocity shift with the Dopplers, like the police on the highway with their speed guns. The change in the frequency of the radar is giving you the velocity of the car. So here it's giving you the velocity of the current. And so that's basically the story. And one thing I just want to, so we're part of this. You had many talks about operational satellites, which are part of Sentinels and Copernicus. ESA is also launching research experiments, and SMOS was one of them. It was the number 2 in the series. Then we had Cryosat, and they are now deciding today and tomorrow about what will be number 9, and so we have this proposal for SKIM, which maybe will fly in 2025. And I just want to show you, what it looks like in the end. I'm just going to skip all that, blah, blah, blah. So if you actually take some model outputs, yeah, maybe it's going to be easier, of the Gulf Stream, and you map it with something which is doing some scanning with a funny way, you can actually measure currents in different directions and make a map that together. So this would be a map of currents from SKIM compared to what we have. And if you actually look quantitatively of what scales we resolve, we typically resolve wavelengths which are shorter than 60 kilometers in the Gulf Stream on these kind of things. And the nice thing is that you can measure at the equator. These are currents around the equator. This is one pass. If you put all the passes together with a revisit time of 4 days, you get that. And that's that's pretty much it. And the good thing is, not very easy to see here, but the swath of SKIM would be 300 kilometers, which is about 3 times the swath of SWOT. So hopefully in 2025 we'll get something better than SWOT in 2021. And maybe they will fly together if everything is nice. So that's all I have, and thank you.
Thank you, Fabrice. Questions? Yeah.
Thank you, Fabrice. Okay. What are the ground truth data source for wave height under hurricanes and tropical cyclones?
Okay, so the best thing we have, so we have altimeter data, right? And sometimes there's rain, so we have to flag them out. But
right, that's KU, right?
Yeah, so C-band is better than KU. There's been some S-band also on MVSAT. It's not such. I mean, yeah, I haven't looked at that too carefully, but yeah, you're right. I mean, there's that's one place where maybe we have to look back at the C-band data more than the KU band. Other than that, what we have from hurricanes is the far field. We have swell going away, and we have SAR measurements of all these swells, and you can combine the swell going away with the altimeter measurements closer to the storm to get a better idea of the storm. But yeah, that's what we have today.
Thank you.